All right, thermal energy, section 5. Atomic view of thermal energy. This is kind of a short section. So, hot object, the atoms and molecules in the object are bouncing around off each other quickly. They're fast moving, lots of kinetic energy, lots of elastic potential energy. The cold object, slow moving atoms, little kinetic energy, little elastic potential energy. So, they're jiggling around a lot more than in the cold object. So, two things. The atoms are moving faster in the hot object, they have higher kinetic energy, and each atom in the hot object will move farther. They stray farther from equilibrium, leading to greater stretching or compressing of the spring like molecular bonds. So, that means each atom has an average higher potential energy than the cold object. So, that's what the diagram is trying to show. Each of these little arrows that we're showing here is longer than each of these arrows on the other diagram. So, that's the idea. Jiggling, great word to describe this. So potential energy stored in any one bond and the kinetic energy stored in any one atom are both very, very small, but there's a ton of atoms in something. So all of these tiny kinetic and potential energies are the sum of what we call thermal energy. So E sub TH. Increasing the object's thermal energy corresponds to increasing its temperature. So in the little picture here, we have a thermograph. These are really cool, by the way. If you've ever had the opportunity, or if you ever get the opportunity to look at one of these, um, we drag a box across the floor. The box is very cool, so it has this cool blue temperature. The surrounding, whatever that is, the ground or a table or something, slightly warmer, so we get this green. But when we drag it, we get this friction that's being created. So we have this heat now, so yellows and oranges and reds. So the thermograph is revealing the hot and cold spots. The heavy box is being dragged across the floor, so the friction is causing the thermal energy to increase. So we get this different color situation going on. If you have, depending on the quality of the goggles or whatever it is that you're using for the thermograph, you can actually see footprints from people who have walked past because of the tiny amount of friction that's generated from somebody walking along the floor. And as over time, the footprints will disappear, but depending on the quality of the goggles that you're using, you can pick that up for a very long time after. You can see all these footprints. And the same would be true of some animal at night, walking. You could see the footprints for something that you would never be able to see, during the daytime, or even if it's during the daytime. You would never be able to see those footprints. Pretty cool. So, how friction causes an increase in thermal energy. So, on this first one here, we see the two kind of rough surfaces. It doesn't even have to be like a rough surface. That's just, if we have a microscopic view of something, we would have these two surfaces that are not totally smooth. So atoms at the interface push and pull at each other as the upper object slides past. The spring-like molecular bonds stretch and store elastic potential energy, and then the bonds break, and the elastic potential energy is converted to kinetic and potential energy of the atoms, so they're like jiggling around. So that's our thermal energy that's being created there. So that's what's going on. The interaction between the surfaces leads to friction, also leads to increased thermal energy of the sliding surfaces. So to find an equation for the change in the thermal energy, we go back to that box that was being pulled by a rope at a constant speed. We've seen that problem so many times over the course of the year. The system is that box plus floor situation. Okay, so the rope exerts a constant force F. So we have friction force to balance the pulling force of the box from the rope. So that is we have F in one direction, we have F sub K then for our friction force. As the box moves through some displacement, we have D for our delta X. The rope does work on the box. So we have this equation now here. Work equals F times delta X equals F sub K delta X in the other direction. So there you go. The work represents energy transferred into the system. So the system's energy must increase. So because we're adding work or we're doing work on the system, the energy is increasing. We saw that back in the beginning of the chapter. We know that the kinetic energy isn't changing because it's not speeding up. So neither is potential energy. So the increased energy must be in the form of thermal energy. Therefore, we can say that we have this situation here. So let me just go back real quick. Let me see if I can put both of these on the same screen. Yep, there we go. So the work represents the energy transferred into the system. So that's this statement right here. So the system's energy must increase because we're doing work, right? So we know the kinetic energy isn't changing because we're not speeding up or slowing down. Neither is the potential energy because we're not going up or down. So then something must be happening here. And the thing that's happening is this guy. Okay, so because this is happening, we have this. So because of this, and this equals this, we can directly turn that into this. So the energy is distributed between the two surfaces in the system, the box and the floor. This equation is valid for any kind of opposition force that is converting work into thermal energy. So that's a drag force, for example. We can even use it in situations when our sliding box comes to a stop. So remember our work energy equation. We always come back to that. I keep reminding you guys. Our full work energy equation is this guy. So this is delta kinetic, the change in kinetic energy plus the change in potential energy plus the change in thermal energy equals work. So if we did have a change in kinetic, if we did have a change in potential and our change in thermal right now, all of that stuff would add together to equal our work that's being done. In this case, we just have a change in thermal. So how much energy does it take to swim a kilometer? So we have a 70 kilogram swimmer competing in a 1 kilometer swim at a steady 1.4 meters per second. That's pretty good. We can assume a typical data for a swimmer moving through the water. So the frontal area is 0.08 meters squared, the drag coefficient of 0.45, density of the water 1,000 kilograms per meter cubed. By the way, I used to be a swim coach, and if I could get my swimmers to go 1 meter per second, if they were going 1 meter per second in the long distance swims, it would drive me nuts. Like, we have to go faster than that. So 1.4 meters per second would make me pretty happy. So this is pretty good. Okay, so what do we do? How much energy is required? Energy. We have something mentioned here that we haven't seen in a very long time. Drag, yeah. So we have this formula for drag that we saw a long time ago. D equals 1/2 the coefficient of drag times, that's rho, density, A V squared. So that one comes back to life. And then we have our energy. This is thermal.
The kinetic times delta X.
Friction, right?
Yeah.
Okay, but friction in this case is
The water. No.
Drag. Yeah. So it's going to be capital D for drag. So this is the friction force, but in this case, it's drag times delta x.
So 1,000 meters is delta x.
Yeah, 1,000 meters for delta x this time. Okay. So what do we know? Delta x is 1,000 meters. Okay. And what else do we know?
Is the A the 1,000? Oh, that's
The cross-section area.
Yeah.
So capital A is 0.080 meters squared. What else do we know?
The weight of this far.
Okay. So mass is 70 kilograms.
The velocity is 1.4.
Okay, V, 1.4 meters per second.
Coefficient of drag.
Yep. Coefficient of drag is 0.45. It's a coefficient. There's no units on that one.
And then rho, is that 1,000?
Rho is the density of water. Kilograms per meters cubed. So that's all the information they gave us. We know coefficient of drag, we know rho, we know A, we know V. We just need to calculate the drag, and then we'll have delta x, right? So all of this here can be substituted in right there, and then multiply by delta x, and we'll have E thermal. So we have 1/2 coefficient of drag, rho, A times velocity squared times delta x. So I can plug everything in. I have 1/2 coefficient of drag, rho, cross-section area, that's a 2, and then velocity squared, oops, not squared there, squared here, and then delta x. Okay, well, I can check the units. We'll have, let's see, meters. We have meters being squared there, so that's meters cubed, divided by meters cubed there. So that meters, and that meters cubed is gone. So we're just going to be left with meters squared on top. We have kilograms. We're going to have per second squared on the bottom. So kilograms, meters per second squared. That's going to be a Newton times meters. Newtons times meters. What is that?
Or
Newton meters? Is that joules?
Yeah.
Is that energy?
Yeah.
Perfect. Okay, so what's our number?
$25,200.
25,200?
One half times 0.45 times 1,000 times 108 times 1.4 times 1,000.
You got to square the 1.4.
Yep. $35,280.
Joules. And significant figures on this would be 35,000 joules. There you go.
That's good. That Olympic guy that fell.
Michael Phelps. Around 4 minutes.
Is that fast?
Yeah.
Okay.
Swimming
Like
for
under
4
4
minutes
minutes.
is
Huh?
swimming for 4 minutes that fast. Takes skill.
Yeah. Like, and so he was probably under 4 minutes. The guy on my swim team in high school was doing it in 4:30 something. He was pretty good.
That's
Block with initial kinetic energy of 4 joules comes to rest after sliding 1 meter. How far the block slides if it had 8 joules of initial kinetic energy?
I'm gonna say B.
yeah.
You're saying what?
B.
How you coming up with B?
Proportions.
Okay. How are you able to do proportions?
4/1 equals 8/x. You cross multiply and you get x equals 2.
Well, how are you able to say that it's proportional in the first place?
Yep. I feel like we need to use one of our equations. That's going to give us a hint.
Is there work being done on this?
No,
How do you know?
because it has an initial. There's nothing being put in.
Nothing's being put in. Okay. So kinetic plus thermal equals 0. We're not adding any potential. So kinetic plus thermal equals 0. Agreed?
Mhm.
Okay. So if I can say that, then I can say thermal equals that.
Yeah.
Okay. Now what?
What does K equal? What does it just equal K?
I have initial kinetic energy of 4 joules. How far would it go if how far would it go if I made it 8 joules instead? So what happened?
And energy was doubled.
If I doubled? So basically if I doubled this,
You have to double the other side.
Yeah, it is proportional.
then I would have to do the same there,
Double
right?
that.
So then I would have double that, yeah?
Yeah.
So if I have 2 that,
That means you're gonna have
the friction didn't really change, did it? So what has to double then, or what has to happen here?
double the.
I have to put a 2 there, don't I?
Mhm.
Okay, so then if I went 1 meter in the first place, then I must have to go 2 meters in the end. Okay, so that's kind of the idea there. All right.